So our final unit of study in this class is going to be looking at what is known as chemical equilibrium, a way of redescribing the idea of the chemical reaction going from reactants to products into more of an understandable way with respect to how the particles actually act going from reactants to products and what is the physical properties or the physical states behind them. So before we can talk about the concept of chemical equilibrium, we have to discuss a couple of other concepts in order to build a foundation, which we will then will spring from describing chemical equilibrium. It turns out that reactants going to products in chemical reactions have to go through what's called a collision process. They actually have to collide. This is known as the collision theory in chemical reactions, where our molecules or atoms must actually collide with one another in order to form products. So if we look at a typical reaction, we start with two reactant particles, and they are moving towards each other at a particular rate of speed, at which time they collide. And when they collide, in order to move towards products, they have to have what's called a productive collision. So we can have an unproductive or a productive collision. If we have a productive collision, we get what's called an activated complex. Now, this signifies sort of a midpoint between reactant and product. It is both and neither. After this productive collision, we end up with forming the products, meaning we have the making and or breaking of chemical bonds occurring during the activated complex phase. And then we end up over on the right-hand side with our products being formed. So it really is the activated complex which is of most importance here. It is at that midpoint in a productive collision where we have attributes of the reactants and the products, so sort of that both and neither sort of thing. And we can represent that graphically through a somewhat familiar graph, but with an extra component added to it. Down below, we see those three points within the reaction. On the bottom, we see the reactants moving towards one another, going through that activated complex, and then moving towards products. Now, the reactants and products side of things is quite interesting here because we've seen this before through our reaction coordinates. Over on the left-hand side, we have our internal energy with respect to the bond structure of the reactants. And over on the right-hand side, we have the internal energy with respect to the bond structure of the products. Now, the difference in that energy between reactants and products is whether we're going to have a reaction release energy, which is shown here, that's an exothermic reaction, or to take in energy from the surroundings, which would be the reverse of this, signifying an endothermic reaction. What is different here is what we see in the middle here now, this hump going over here. We didn't account for that before. That is known as the activation energy of the process. It is an energy barrier which must be overcome in order for reactants to go towards products. So in this case, this exothermic reaction is not just a downhill trek from reactants to products. It's not spontaneous. We have to put enough energy in order to gain that back, plus a little more to make this an exothermic reaction. So it's this activation energy that must be overcome in order for reactants to be converted to products. This activation energy, this energy barrier, can be expressed sort of with an analogy. If you see with this sort of marble moving towards this hill right here, and if we have enough kinetic energy with respect to that marble, it can make it up and over the hill similarly to the analogy is going over that energy barrier, going from reactants to products. So we have to have a certain amount of kinetic energy in there. Kinetic energy is the energy of motion. If we flick this marble fast enough, it's going to make it up and over that gravitational energy hump and be able, in this case, to sort of typify going from reactants to products. If, on the other hand, we had a situation where that marble was not moving as fast as before, and we encounter this sort of hump or this gravitational barrier, it's possible that that marble could make it almost to the top, but then not quite, and then roll down the other side. This would be analogous to an unproductive collision. There was not enough kinetic energy being converted into activation energy for this, so that the reactant particles would bounce off one another and still remain as reactant particles, because the energy imparted by the kinetic energy was not converted into sufficient energy to make and or break chemical bonds to make it over that energy barrier towards products. Another very important concept to define here would be the rate of a chemical reaction, defined as the amount of reactant that is converted to product in a given amount of time. Now, perhaps we've implied throughout the course, when we're talking about chemical equations of reaction in general, that these reactions are instantaneous. Reactants go to products, and it may seem like they are instantaneous. At least that's the way we're putting it across in our descriptions. And some chemical reactions may indeed seem to be instantaneous. No sooner do we pour or we mix two reactants together does the product form. Very similar to that lab that we did, where we drip in some reagent, and immediately this precipitated product comes out of solution. It seems to be instantaneous. Well, nothing is instantaneous. It's just a very, very fast reaction rate. The amount of time going from reactant to product is so quick that it appears to be instantaneous. So what we have here are two different reactions which we're going to track comparisons of their rates of reaction. So some reactions, as we said, can appear to be instantaneous, but will actually have a very fast reaction rate. That's going to be the reaction on the left-hand side. So if we start at time equals 0, we see in this box over on the left, we see a bunch of blue and red orbs. Those represent the reactants in this reaction. And before hardly any time has passed, we see the product that those green ovals in there is starting to accumulate, so that this really forms product very, very quickly, and towards the end of this time process, we're just sitting around with a lot of product in there. So reactant to product went very quickly. That rate of reaction was very fast. Contrast this with the reaction on the right, is reaction with a slow rate. And of course, at t equals 0, we will see that some reactions are very, very, very slow. They can take hours, days, or even weeks for the reaction to go as far as it's going to go. So here we have a box of purple and yellow spheres signifying time equals 0 in this reaction. And as we move along that same timescape, if you will, we find those brown ovals, the products are being formed. They're being formed at a much slower rate than before, so that at the end of that given amount of time, there's still appreciable amounts of reactants left over. That reaction is not done. It could take, that's the type of reaction that may take an hour or a day or even weeks to complete, because its reaction rate is much slower compared to the reaction we saw on the left. So the rate of reaction can be observed to go faster or slower for a given reaction based upon different environmental factors. Essentially, the rate of chemical reaction depends on the number of productive collisions of reactant particles which occur in a given amount of time. That's essentially what we said before as the definition of reaction rate. But we can tune reaction conditions such that we can optimize the rate of a reaction. Almost always for a chemist, we want to optimize the rate of reaction, increase that rate, because we have things to do, and we don't have time to wait around all day or all week for a reaction to occur. So we can work towards decreasing the amount of time it takes for reactants to go to products. In essence, increasing that reaction rate. So we have three ideas which can can increase the rate of chemical reaction. The first is that we can increase reactant concentrations, the concentrations of the reactants themselves that will spur a quicker reaction rate. Similarly, we can increase the temperature of the reaction, or we can add a catalyst to the reaction, which we will explain presently. The first concept, to increase the reactant concentration. Let's take a look at two different scenarios. The first one would be at low concentration, where this graphic shows the reactant particles in a low concentration condition. The reactant particles are very far apart, decreasing the likelihood that any two of them at any given time will collide, and much less having a collision that's productive. And that results in an overall lower reaction rate than, say, the next one we're going to look at, where we have a high concentration. This sets our reactant particles much closer together, by comparison, increasing the likelihood of a collision, and hopefully a productive collision, between them. Of these two right here, we can say that the one on the bottom increases the likelihood of collisions, and thus an overall higher reaction rate compared with the lower concentration. The second one, increasing the reactant temperature, the reaction temperature. We have a graphic here where we show the differences in kinetic energies. This should be somewhat familiar from our discussion on evaporation a few units of study ago. But at different temperatures, we have different arrays, or at any temperature really, different arrays of particles within a solution moving at a particular speed or kinetic energy. We can have no matter how hot or how cold a solution is, of the particles within it, there's some moving very slowly, some moving very quickly, and we also have an average. However, just like we saw with evaporation, there's always a certain number of these particles which are at or above a certain kinetic energy that will allow for a productive collision. So let's keep our eye on the fraction of the area under that curve of particles which can, if they collide, impart sufficient kinetic energy to get us through our activated complex. And we'll look at two different temperatures here. And remember, a higher temperature sort of flattens the curve, if you will. So if we have a situation where we have up at the top where our second temperature, T2, is greater than T1, we can see the T2 sort of is flattened out here. And what that does is it increases, if it flattens down from the top, it increases to the sides. And the important thing to keep in mind here is this at or above a certain kinetic energy to allow for a productive collision, we get a higher number of particles at or above that kinetic energy at any given time. So the lower temperature, the number of reactant particles at or above this sufficient kinetic energy for productive collision, there's not as many of them. They're lower than that of a higher temperature, which results in, if there's more at the higher temperature at any given moment, it results in the higher temperature reaction having the higher reaction rate. Lastly, we can add a catalyst to a reaction. Now, a catalyst, by definition, is a substance that, when added to a chemical reaction, accelerates the reaction without being changed or affected itself. So, if the catalyst remains unchanged, it remains in the reaction to continually mediate that reaction at a faster rate, which is why when we add a catalyst to a reaction, we only need to add a very, very small amount, because each catalyst molecule or particle can continually move reactants to products at a faster rate. So why does this catalyst, as opposed to an uncatalyzed reaction, why does this allow for a faster reaction than an uncatalyzed reaction? A catalyst, it turns out, decreases the activation energy of a reaction. To look at it graphically, so on the graph here, here is our activation energy for the uncatalyzed reaction. Here is the activation energy for the catalyzed reaction. It is much lower. And if we lower the barrier, it makes it easier for these reactants to go to products through a productive collision. We don't have to collide at such fast speeds that all that kinetic energy is converted to activation energy as much, because we have that lower curve right there, and we are able to send more reactant particles towards products at any given time, because it's more energetically favorable to do so. So now we're ready to discuss what chemical equilibrium actually is. And in so doing, we have to rethink our concepts and ideas of reaction directionality. So in a chemical reaction, we're always trained to have, well, here's our reactants, there's the arrow towards our products, it is one way. Well, remember when I said in class that directionality isn't absolute in a chemical reaction. If you can show me a chemical reaction in one direction, I can probably come up with reagents and conditions to send it back the other way. All reactions are inherently reversible. So let's think of it in that manner as we move forward and think more about this idea of reaction directionality. So really what becomes is our reactant profile going one direction to product profile. Well, now it's sort of reactants going to products. At the same time, we have products reforming reactants. Now that flies in the face of any understanding of a chemical reaction, but that's really what's going on here. There's always sort of reversibility in a chemical reaction as it's going. And the stopping point in a chemical reaction, we're going to find, is not all the way to products all the time. The chemical reactions that we've been going over in this course and being used as examples are especially cherry-picked to be ones in which the reactants indeed go all the way to products. That's not always the case. Sometimes chemical reactions stop right in the middle, where we have appreciable amounts of reactant and product left in the reaction pot. And that's what we're going to be looking at with respect to chemical equilibrium. So in any chemical reaction, we allow it to progress, and it reaches what's called dynamic equilibrium, meaning that the rate of the forward reaction that we are very comfortable with at this point is the same as the rate of the reverse reaction. And in so doing, we have a tie, really. It means that there, at any given moment, once we've reached dynamic equilibrium, there is an appreciable and unchanging amount of reactants and product profile in that reaction mixture. So let's track the progress of a given chemical reaction using or keeping in mind this idea of chemical equilibrium. What does this actually mean? We'll try to tie this in with reaction rate. Well, every reaction has a 0 point, a time where it's technically it's the starting point, where all we have are reactants in the reaction that is poised to move. So here we are at T equals 0. The reaction has not yet started. And now we're going to sort of move through different points in this reaction where product is starting to be formed. So here we have our next step. Our reaction just begins. We're just starting to form our products, and the reaction rate is at its highest. Now notice, as soon as products begin to form, we get the reaction starting to go back the other way. Not much, hardly at all in the very beginning, which is why the net reaction, which is the difference between the forward reaction and the reverse reaction shown here, is at its smallest. It's almost completely forward reaction. But as we move forward in this reaction cycle, the reverse reaction rate becomes more and more. So as reaction is progressing, we get the rate of forward reaction slowing down and the rate of reverse reaction actually increasing. And the net result of that is that the overall reaction rate from reactants to products slows down, or appears to slow down, until we get to what is known as dynamic equilibrium, where the overall reaction rate is 0. Why? Because the rate of the forward reaction, which is always happening, even when it appears to be done, is the same as the reverse reaction rate, which again is always happening. The net result of that is a 0 reaction rate. So to bring in the important concepts here, a reaction rate, the overall reaction rate, will slow down over time due to the increasing competition of reverse reaction. And at equilibrium, we have overall reaction rate equals 0. Now this looks sort of dodgy, because it appears that at any given indication, at least by the way we're looking at it here, that any reaction can't be more than 50% effective. Well, that's not true. In this particular example case, we have a situation where this at dynamic equilibrium, where the reaction rate is 0, we have appreciable amounts of the reactant profile and the product profile. But that's not always the case. At equilibrium, the amounts of reactants and products are not necessarily equal. We talk more about whether a reaction's equilibrium favors reactants or favors products. For us as chemists, any chemical reaction whose equilibrium favors products is something we like. We want to form products in a chemical reaction. We don't want to sit around and just have them go a little bit and have mostly reactants in there. We want to design reactions such that we will force as much of our reactant profile towards product profile as possible. So let's look at some examples. So here's an example of where a reaction's equilibrium heavily favors products. Sodium plus chlorine goes to sodium chloride. So that's table salt. So when you look at your table salt container, sodium chloride, in the dining hall or something, that's table salt. You don't think of it as anything else. However, there is at any given time a certain amount of that table salt being converted back to sodium metal and chlorine. Now, it's a vanishingly small amount, since this reaction's equilibrium heavily favors products, but it happens. And as soon as they're formed, the same rate of reaction converts them back to sodium chloride. So you don't have to worry about sodium metal or chlorine gas being in your or at least in your sodium chloride or your table salt at all. It's because this particular reaction's equilibrium heavily favors products. Why? It just does. And at this level of play, I would have to tell you whether one particular chemical reaction whose dynamic equilibrium favors reactants or products. So let's look at another one. Here's an example of a reaction whose equilibrium heavily favors reactants, NaHCO3. This is baking soda. is always in some sort of dynamic equilibrium with this product profile here, sodium hydroxide and carbon dioxide. Very, very, very little amount of that forms, and when it does form, it's immediately converted back to our baking soda, if you will, product. But in this case, this reaction's equilibrium heavily favors the reactant profile. So if you have your sodium bicarbonate and you're putting it in your cat's litter basket, you don't have to worry about it forming carbon dioxide and sodium hydroxide, at least not to any extent where your cat would be able to figure it out. So let's say we encounter a chemical reaction that has a really crummy equilibrium, meaning it sort of stops right in the middle. We have appreciable amounts of reactants and products at this dynamic equilibrium. That's not good for us as chemists. We want to carry out chemical reactions that go all the way to product, whose chemical equilibria always favor product. But we don't know how that's going to occur if it's the first time we're trying to invent a product or come up with a new chemical reaction that's never happened, that nobody's ever done before. It occurs a lot in chemical research, because in chemical research you're always coming up with these new reactions, and you don't know where that particular new reaction's dynamic equilibrium is going to end up. Will it favor reactants? Will it favor products? Gee, I hope so, but it may not, or may stop sort of right in the middle, where there's appreciable amounts of reactants and products at that new equilibrium. Well, we would like to find ways of tweaking that towards products as chemists. If we encounter a reaction whose equilibrium is sort of stalls out in the beginning or halfway through, we invoke we use what's known as LeChatlier's principle, given up top here. The definition of which is, if a chemical reaction that's already at equilibrium, that's important, it's already stopped, is subjected to change, the reaction will find a predictable new equilibrium. So what is that change that we were talking about? And what is the predictable new equilibrium we would like? Well, we would like a crummy equilibrium, this predictable new equilibrium, to be more towards products. Thank you very much, because as a chemist, I want to optimize my amount of products and minimize the number of reactants that are left over in this particular reaction. So what does this ultimately mean? A good way of expressing LeChatlier's principle is through a model. Just make this model up in your mind. I've drawn a picture of it. It's two glass beakers, and we have gone to a glass shop and put a hollow tube between them. It's that hollow tube, and then filled them with water. Filled them both with water. Indeed, we could fill only one with water, and if we filled the one on the left with water, well, that water would sort of squirt into this other beaker until both of the levels were equal. Why? Because we get this sort of, we can have this back and forth through this glass tube connecting the two beakers. So the beaker on the left signifies our reactant profile, and the beaker on the right signifies our product profile. And here we are at an equilibrium. And this would be an example of a crummy equilibrium, in which we have sort of the reaction has halted with appreciable amounts of reactant as well as product. So ultimately, what can we do? What change can we do to it? Pretty much overwhelmingly, the change we're talking about is added or subtracted concentrations of these reactants or products. If I add extra reactant, one or the other, so that would increase the concentration of that reactant, it would push our equilibrium towards the right. We always want it towards the right if we possibly can. So let's look at that. Here we have a situation where we would, if we had perhaps a solid product that was crashing out of solution, like a precipitate as it was formed, and say we were able to have a way of fishing out that one solid product as it was being produced, that would lower the concentration of that product in the product profile. And if we did that, that would be similar to taking out some of the water in this product profile of these beakers. So you would ask yourself, what happens if I take out some of the water in the product beaker? Well, I'll show you what's going to happen is we're going to get a flow in that glass tube, and that flow is going to be to the right. That is an analogy for the reaction is then going to be pushed towards the right, towards products in this case, in this analogy of a beaker example. Another more, probably a better way of doing that would be with respect to one of the reactants. If we have our crummy equilibrium, what can we possibly do? Well, let's get a situation where we're just going to swamp it with another reactant. If we have this maybe the cheaper of the two reactants, and we just hammer it into that reaction vessel, what that does by analogy is we increase the water in this reactant profile beaker. This beaker doesn't have the reaction going on in it, but it's to indicate this predictable new equilibrium. Which way will the equilibrium shift? Well, if I put a whole lot of water in this left-hand beaker, it is going to, again, move water this way through that tube to compensate, and that is an analogy towards making more product, ultimately. Building a higher concentration of product just by bumping up the concentration of one of the reactants. So to put this idea to actual work, this happens, as I said, frequently in much chemical research where reactions are being discovered or tried that have never been tried before. So it's really a crapshoot as to whether you're going to have a reaction with a favorable equilibrium towards products or a not so favorable equilibrium sort of back towards reactants or stopping somewhere in the middle. We can use LeChatlier's principle to our benefit. And let's say we're right at the end of a long process. We're about to come up with a blockbuster drug. And our last step in the process involves the reaction. Our reactant profile involves a very expensive reactant, perhaps one that we've worked on for a number of steps, and this added very cheap reactant. And we find out that this reaction has what's called a suboptimal equilibrium. Let's say it stops in the middle, or it doesn't really get going that much. But we would like to maximize the amount of our blockbuster drug that we get out of this process. What can we do? So we're stuck sort of in the middle where we have appreciable amounts of that blockbuster drug, but we also have appreciable amounts of these reactants left at this very unfavorable equilibrium. Well, why don't we take a whole bunch of this very cheap reactant and swamp that reaction with it? And that is going to shift that equilibrium more towards the desired product formation. Essentially, we're going to use up the rest, as much of the rest of A as we possibly can, because we keep hammering it with this very cheap reactant, B. This sort of strategy is applied frequently in these situations where we're trying to maximize the formation of a particular product and minimize any residual reactants in the mix. Well, we'll just swamp it with the cheapest reactant, and through LeChatlier's principle, send that reaction towards product formation. So it turns out there are actually two factors which can affect an established chemical equilibrium. We looked at differences in concentrations. That's the first one, which we'll take a look at. We have to be at equilibrium first, and how can we shift that towards products? Well, remember what we did was we added more of the cheaper reactant we saw on the previous slide. So we changed in the concentration of a reactant or a product. Remember, we could bring down the concentration of a product in order to shift a reaction to the right. But an example of this might be hydrogen plus iodine going to 2-hydroiodic acid. And this particular reaction has, depending on the temperature, an unfavorable equilibrium. Well, what can we do to maximize product formation, well, let's just hammer it with excess reagent, and what that will do will be to send that equilibrium, or shift it rather, towards products. But by adding reactants and products, or taking away products, is not the only way to affect an established chemical equilibrium. And this goes back to our original study of what components do we have in a chemical equation of reaction. We are always concerning ourselves with the matter side of things. But remember, matter is anything that has mass and takes up space, but there is always an energy component of a chemical reaction, and we can utilize that too if we know whether it's an exothermic or an endothermic reaction. For instance, this reaction here is an exothermic reaction. I know this because my energy component is on the product profile. It releases energy. If we're an endothermic reaction, that energy component would be over on the reactant side, meaning we require energy from the surroundings for an endothermic reaction. But here is our exothermic reaction, and say we have an unfavorable equilibrium. How can we shift that to the right towards products? Well, let's take a look at what part of our product profile is this energy we see here in the form of heat. We have heat energy, so that what if we took this energy away? Essentially, what if we cooled this reaction vessel down in an ice water bath? That would take away that amount of energy. So if the reaction in this case is at equilibrium is cooled down, then the equilibrium would shift to the right towards products to compensate. So conversely, if our energy component was over here on the reactant side, which would indicate that is an endothermic reaction, that would mean we'd have to maximize. We'd want to maximize the amount of energy on this side in order to send, so that would mean heating it up. An endothermic reaction, we would heat up to send its equilibrium towards products. An exothermic reaction, as we just saw here, we're going to cool down to get rid of this energy, or to take that energy out of there to shift again the reaction towards the right. So thus far, we've been speaking very figuratively about the equilibrium or dynamic equilibrium of a particular reaction, using words like crummy equilibrium, or an equilibrium stopping in the middle, or favoring products, or favoring reactants. And as scientists, we sort of push back on those sorts of things, and we're more interested in actual data, in actual numbers. So we have a way of describing the situation of a particular chemical reaction's equilibrium by using what is known as an equilibrium constant of a particular reaction, KEQ. This is a number. It's a way of expressing a chemical equation's equilibrium in numerical form. So the way to come up with this is we find we have a reaction at equilibrium, whether it's equilibrium favoring reactants, products, or somewhere in the middle, and we're able to measure the concentrations of our reactants and products and plug them into an equation which will give us a number. And it is the size of that number which determines whether we have an equilibrium which favors reactants or products, or the fact that we have appreciable amounts of reactants and products at that reaction's equilibrium. So we use a mathematical equation which uses the formula or the following figurative way of describing a chemical reaction. So we have a lot of lower and uppercase letters here. Of course, it's sort of in the standard form. We have our reactant profile, and we have our product profile right here. So A and B are reactants, C and D are products. Now, the lowercase letters represents numbers, the coefficients. So, you know, so when we were balancing chemical reactions, we put these numerals, these coefficients in front of reactants and products in order to balance it. That's what these lowercase a, b, c, and d's mean. Uppercase is the actual concentrations, molarities of these reactants and or products at equilibrium. And here comes the mathematical equation where we have our concentrations of products over the concentrations of reactants. Now notice with the brackets around each of these things, that signifies concentrations. So at equilibrium, we can measure the concentrations of our products and set them to the exponent, which we see here, of the number in the balanced equation. So we have to pay a little bit of attention to that. And we do that with all of them, and then we multiply that concentration of reactant set to its exponent times to the next concentration of the product. I'm sorry, not the reactant. We always put the products in the numerator in this case, and always the reactants in the denominator. So very important, products over reactants. And when we carry out this mathematical equation, it's going to come up with a number. And sometimes it'll be a very large number, sometimes a very small number, sometimes neither. It'll be just sort of a regular number that doesn't appear to be very large or very small. And this can tell us a lot about the breadth or how much a particular reaction's equilibrium favors products, reactants, or is it somewhere in the middle. So let's talk about the size of the any particular chemical reaction's equilibrium constant. If an equilibrium constant of a chemical reaction is very small, and I realize small can be relative, you know, for one person, well, that's small, and another person says, well, no, it's sort of medium size or large. So we're going to put a yardstick to it. If the equilibrium constant of a chemical reaction is very small, and I'm going to say that's less than 0.01, that's my yardstick, its equilibrium is considered to heavily favor reactants. Fair enough. Okay, we get something less than 0.01 heavily favors reactants. We can say that. On the other side of things, if an equilibrium constant of a chemical reaction is very large, and I am putting the goalposts for large at greater than 100, its equilibrium heavily favors products. And if we're anywhere between 0.01 and 100, that's the rest of that number line, means that there are appreciable amounts of reactants and products present at equilibrium. So knowing this, this information, we can go ahead and do some example problems where we're perhaps coming up with an equilibrium constant in order to discern whether that reaction's equilibrium heavily favors reactants or products or otherwise. It is important, before we get into doing some problems with this, to define a constraint on this process. One of which is that the physical states of the reactants and products are important. So here we have in parentheses G for gas, S for solid, G for liquid, are very important when deciding whether or not these reactants or products will be used at all in the equilibrium constant equation. So there's 4 physical states, solid, liquid, and gas, that we're concerned with, as well as the dissolved state, AQ. That usually expresses the a dissolved state within water as a solvent. Of those 4, only 2 are included in the equilibrium constant equation. If we have the gaseous state or the aqueous state, those are included in an equilibrium constant equation. If, however, they are put into a solid or as a liquid, they are to be completely ignored. Now, one last thing, this is a sort of a standard chemical equation of reaction showing, as we saw before, those physical states. Remember, we said sometimes they're used. This is one example where indeed they are used. But in here, it's also showing the temperature of that the reaction is carried out with. And that is because the equilibrium constant is different at different temperatures. It's heavily dependent on the temperature under which a reaction is carried out. So if we are providing a problem set or an example problem of a particular, looking for the equilibrium constant of a particular chemical reaction, we always, by convention, show the temperature at which this reaction was carried out. So let's put this particular equation and its temperature into a problem. So we'll consider the following reaction at equilibrium. This was the same reaction and its temperature that we saw on the previous slide. And now we're given some extra information of concentrations. So if the concentration of C2H6, which is one of our reactions, at equilibrium is 1.71 molar, and chlorine, the other reactant, is also 1.71 molar, and the concentration of HCl in this case is 0.29 molar. What is the equilibrium constant for the reaction? Notice they don't give any information about this product. And the reason why is because it is in the solid state. We ignore that, and we will indeed ignore that in our equilibrium constant problem. Thus, our entire product profile that's going to be recognized and plugged into the KEQ equation is just HCl because it's gaseous. Gaseous is a state where we do include that. We don't include this C2H5Cl in any way, shape, or form, and we'll see that as we move forward. So this is how we would set up our KEQ equation. Notice the products on the top is only HCl, as we just referred to, and we put our reactant profile on the bottom. Now notice on all of these, our numeral implied in front of our reactants and products is 1. It's not shown, but it's that is the implication. So we put these to the first power, which means you don't really even need to do it because anything set to the first power is that original value or original number in the first place. But we're just setting this up the proper way, and we just plug in these values again using only the values which were in this case gaseous, and we'll plug in the numbers, and there it is. Products over reactants. Once we carry this out, it comes out with our number, which is going to be our equilibrium constant, 0.10. Now this number, 0.10, is between 0.01 and 100. So this would be an equilibrium constant that would tell us at this particular temperature that there are appreciable amounts of reactants and product at equilibrium, and indeed there is. So let's look at another example which will highlight the idea that we can approach an equilibrium constant problem and ask many questions, not just the questions that we had in the last one was calculate the equilibrium constant, but we can really trim around the sides and recognize that this particular mathematical equation is amenable to asking other questions. So consider the following reaction at equilibrium. H2 plus I2 goes to 2HI. Notice they're all in gaseous states, so we're going to be using all of them. Now notice it also gives an equilibrium constant, 69, temperature at 340 degrees Celsius. That's done by convention, as we know, because equilibrium constant is highly dependent upon temperature, and we get some information. If the concentration of both reactants are 0.02 molar, what is the concentration at equilibrium of our HI product? So this is different than the last time. In the last one, we had to calculate KEQ mathematical equation. In this one, KEQ is given, but we're asking for the concentration of HI. Well, let's set this up. How are we going to set this up so that the concentration of HI is all on one side? Well, here's our equation that we have here, and we want to solve for the concentration of hydroiodic acid. So how are we ultimately going to do that? Well, we set it up such that, and then again, algebraically we maneuver this such that HI squared, why is that squared? Well, because that 2 on there comes from the fact that we had the numeral 2 in front of it. And our exponent 1s, which we see down on the bottom, or on the H2 and I2, are because that numeral was an implied 1. So that's why we have that HI squared. So how are we going to do this? Well, to carry this out, we first we want the concentration of HI. I don't want the square of the concentration of HI, just the concentration to, say, the first power. So what I'm going to do is I'm going to take the square root of both sides, now removing that HI squared down to HI, and we'll just plug in the numbers. Once we do that, we carry out the operations in the parentheses, take the square root, and ultimately end up with our number. The concentration of HI is 0.17 molar. Full stop.